Hello, good morning, everyone. Can everyone hear me? Please give me a yes, no. Can anyone hear me, please?
Yes, sir.
Great. So, yeah, how do I share my screen in this? Okay, share content. And here I am. Okay, so I think. Okay, so we'll get started, right? Everyone can hear me loud and clear, right? Okay. Yeah. Okay. So how many? So not many attendance, but that's okay. So we'll get started, or shall we wait for another 1 minute before we get started?
We can start, sir. We are recording anyway.
Okay.
I mean, you
Yeah.
are recording anyway.
Yes. Correct. Okay, so let's get started. So you can see my screen, right, which says piezoelectric transducers and the name of the course, instrumentation devices 2, and my name. The screen is visible to all of you, right?
Yes, sir.
Okay, great. So let me see. So let's look at the contents. What all we are going to discuss first in the next few classes. This is not the contents of the overall course. So we are going to discuss actually piezoelectric devices, and we are going to first look at the importance of such devices in the modern world, because this I think is very important in setting the context, right? Because whatever we are learning as engineers, there has to be a good application. There has to be a meaning towards it, right? There's no point we as engineers we will be working on devices, or we will be developing devices or making new products which will go straight into the market. So looking into the subject in the context of business, in the context of the global market, that is important. We'll have a brief look at that. We'll look at the history a little bit, how this subject kind of, or how piezoelectric devices came into being. We'll look into the material structure in somewhat detail. Look into the fabrication, very fleeting, quick discussion on fabrication, not too much in details. And then we will discuss what is a smart material and the significance of it. And then we are going to start going into the theory, the real mathematical theory and analysis of such sensors based on piezoelectric material. And then we are going to discuss figure of merit, meaning based on what parameters we can quantify or qualify that, okay, this sensor is good in so and so aspect or not so good in so and so aspect. So that's what we call as figure of merit. And then we're going to look at some applications. We're going to look at specifically ultrasound or ultrasonic transducers in detail, and we will have a fleeting glance of a few applications based on piezoelectric material. Okay, so global market trends. So this is where we stand. So as of 2021, it's just the piezoelectric device market is around $29 billion. And by 2026, you can see it's going to be upwards of 35, with a cumulative average growth rate of 4.5%, which is decent, which is not bad actually. And the key growth drivers are the aerospace industry, defense, automotive. Automotive, of course, is booming with all electric vehicles, or more and more autonomous driving that you see coming to the modern cars. Automotive is, of course, booming. Healthcare, and then these days everything we are trying to tie it to the internet, and that's what we call as Internet of Things. And in terms of product classification, we can see, so the first few Raju? Hello? Sorry, I don't know if I was muted. Hello? Hello? Sorry if I probably talked while I was unmuted. Can you hear me?
Yes, sir. Now we can hear.
Yeah, sorry. Okay. I think I talked while I was unmuted. So in terms of products, piezoelectric materials, you will find them in sensors, actuators, motors, and of course, transducers in general sense. And we're going to have a look at quite a few of them. And the way these products are made is like, crystals, ceramics, polymers, and composites. Composites are essentially, a mixture of, I shouldn't say mixture, it's kind of made using, more than one kind of material. So this is what, the materials that are typically used. These are just, by the way, some general broad overview, so nothing to sweat about. This is just for setting the context and get the ball rolling. Okay, so yeah, so as you can see, this thing was this phenomena rather was discovered by French physicists in the year 1880, so quite some time back. And it was discovered in quartz crystal. So on the left here, these are some quartz material, quartz crystals. And this is actually the crystal structure. We're going to have a look at this in closer details in the next few slides. And in the very next year, one gentleman by the name of Lippmann, he, talked about the inverse of piezoelectric behavior. I mean, as we can figure out, right, it's kind of obvious that, which is the first to be discovered, right? I mean, typically we deal in the real world using force or pressure or, whatever. And then we see how the material behaves, right? And the inverse is kind of not so straightforward. The inverse typically happens because of curious and tries to study. This was discovered was probably, the physicists they applied some force or pressure to the crystal and saw if there was any electrical behavior that was changed, that was getting changed, or that was exhibited by the crystal, and that's how it was discovered. So the thing to remember, or the key takeaway, and we will keep talking about the direct effect and the indirect effect in the next few slides. So the direct effect means, a force or a mechanical entity, a mechanical component was applied to the crystal. And as a result of the mechanical force application, an electrical behavior was observed, right? So that is what we call as the direct behavior. And by the way, I think Shubham has asked if I'm audible. So Shubham, I'm audible, right, to you?
Yes, sir. Initially, for
Okay,
some
okay.
moment you were in.
Yeah, okay, great. No problem. So, so the inverse was like, if someone applies an electrical signal, then the physical or the mechanical aspect ratio gets modified, right? So that is the inverse of the um, you know the behavior. So which was of course discovered later, right? And some general trivia that piezo, the word piezo comes from the Greek word, which means squeeze or to press, right? So not a big deal. Sorry. So okay, so this is the molecular structure of quartz. So if you see here, so these red guys that you see here, so let's say these are oxygen molecules, and the yellow guys, these guys, these are silicon molecules. So quartz essentially is nothing but silicon dioxide. And if you were to see the, let's say, a set of molecules, let's say you pick up a piece of quartz and you do a crystallography study of the crystal, and you look at the crystal structure from different angles, you will see different views, of how it's the same structure, but what is important is how you are looking at the structure. So from one angle, if you see here, right, you see, so the red guys are the oxygen molecules, and the yellow guys, they are the silicon molecules, right? Now, before I'll come back to this, but before that, so this is another view of the same material. We have rotated it, and we are trying to see this from another angle, right? So here again, what you see is, we have the silicon guys sitting in these. So these are the silicon guys, right? And these are um, uh, the oxygen molecules. So here, for example, if you look at this piece, right, you will see we have silicon molecules sitting here. How many silicon molecules? 1, 2, 3, 4, 5, 6. And here again we have 1, 2, 3, 4, 5, 6. But then if you look at the spatial arrangement, the center, right? If you take this piece, the center for the silicon and the oxygen probably will coincide. Similarly, it will coincide here. It will. So let's 1 second. So, but if you see overall, right? Overall, if you see the center for the silicon molecules and the oxygen molecules, they don't kind of stick to each other. Let me try to show a piece where the centers are not in the exact same structure. Maybe if I go to this slide, for example, if you see in this slide, looking at the same structure from this angle, you will see that, okay, we have one guy here, second, third, and this is the third. I mean, this is one oxygen molecule, this is like a spiral structure. But here, if you see, these guys will have a center symmetry, meaning if we were to plot the center of the silicon atoms and the center of the oxygen atoms, it will coincide here at the same point. And what that means is, we'll try to see, yeah. So for example, so the yellow guys, as I said, is the silicon atoms, and the oxygen atoms are the red guys. So if you see in the normal condition, these guys, the center lies in the same place, right? And if we apply pressure, what happens? What will happen is the silicon molecules, you can see it will spread, and so will the oxygen atoms. Sorry, I'm not saying, I shouldn't say molecules, I should say atoms. The silicon atoms kind of spread, right? And if you see the center of the silicon atoms and the oxygen atom, the positively charged silicon atoms or the cations, and the negatively charged oxygen atoms, the anions. By applying a pressure, we see that the centers, they kind of split, right? Which means the center symmetry of charge is lost, meaning earlier without force, when the force was not there, the center of the positive charges and the center of the negative charges, they were coinciding with each other. When we apply a force, because the atoms kind of spread, the center symmetry is lost, and because of which we can say, so for example, now in this case, so this is the positive center and this is the negative center, right? So now, because on the application of a force, we have a let's say negative charge minus q here and positive charge plus q here, right? So we have a dipole that is formed, right? The dipole is formed in this direction, right? So from the negative charge to the positive charge, right? So so key takeaway from the previous few slides is this behavior is exhibited only when you apply the force in certain angles. It will, if you take a quartz crystal and you start putting the force in any orbit direction, right? You are not going to see this behavior. So this behavior is going to be visible only when, let's say, if you look at the plane, right? If you look at this plane, right, on the application of the force, for example, if you go back to this plane, you can have a look at the structure closely between the first three configurations that I showed, right? You can see, you can probably try to, visualize why on the application of the force, the piezoelectric behavior does not show up in the first picture or the second one, but it shows up in the third one. So the key takeaway is that, this behavior is observed only when you are looking at the material in certain angles, right? So which means that we have to, when we are characterizing or when we are talking about this material, we are going to talk in terms of certain axes, right? So the 2D equivalent, so revisiting what we discussed just now. So let's say we have put, we are trying to make a 2D model of the structure. So let's say the big guys are the silicon atoms and the small red ones are the oxygen atoms. So if we make a 3D model from the 2D equivalent, what we can say is, so these hexagonal arrangement of silicon and oxygen atoms. So let's say there are multiple layers of such atoms organized, one on top of the other, right? So that will give us, from a 2D kind of approximation, we are going to go to the 3D kind of a structure. So this is straightforward, right? Any questions up to this point? How the 2D structure? So if you see the same red guy is shown here, the oxygen atoms, and the same silicon guys are shown here, right? And if you see the way I have kind of drawn this diagram, is this silicon atom is nothing but this guy, right? This silicon atom is nothing but this guy, and correspondingly the oxygen atoms you can locate, right? So now if we have multiple such layers, we can kind of think that, okay, this is the 3D structure, right? Straightforward, right? No big deal. So what happens is we first define the optical axis or the z-axis, right? One key point to remember here, this I'm talking in the context of quartz, which is a naturally occurring material. So the z-axis, the way it is defined for, let's say, a ceramic, which is a synthesized or a man-made material, that will be different, and we'll talk about that probably later. But when we are talking of quartz, we can define the optical axis as the z-axis. And if you see here, so if you want to do a little bit more study of what is meant by the optical axis, please feel free to do so. But one thing you can kind of figure out, so the optical axis is somewhere right in the center here, right? So if a ray of light is passed right through the center, it is going to have minimum diffraction or whatever. So because it will not have any obstruction when you are passing the light right through the center, it will not have any obstruction coming from any of the silicon or the oxygen ions, right? So that is the optical axis. And once you define the optical axis, we say this is our x-axis, which is the electrical axis. And once we say that, okay, the first z-axis is the optical axis, and the second on the going towards from the center, it's going towards the right is our electrical axis. And the third axis we define as the mechanical axis. So this is how the axes are defined in quads. And the reason, again, I repeat, these axis definitions are important because the behavior itself is exhibited. The behavior shows up only when you are kind of looking at or studying the material in a certain angle. If you apply the force or the electrical signal in any orbit direction, you are not going to kind of see the behavior as per your expectation, right? So these are the three axes, the way it is defined. Any questions up to this point? Okay, so if we see here, what we established in the previous file, that if we apply a force on the x-axis, so basically our x-axis, so this is our x-axis, this is our x-axis. So if we apply a force, let's say a compressive force along the x-axis, and if we have electrodes, here, so the force is applied in the x-axis, and the electrodes are placed normally. Normal means at 90-degree angle to the x-axis. So these are the electrodes. If we apply a force, we'll get a net positive or negative charge on the plates, right? And this we call as the longitudinal effect. Whereas the key thing to look at so this is a little bit, this needs a little bit in-depth thinking, that when we are applying the force in the longitudinal direction or in the x direction, right, the charge developed. So charge, what I mean by charge is the total charge developed on the surface of these electrodes, right? It is proportional to the force. Or you can say the charge density, the surface charge density developed on these electrodes, it will be proportional to the pressure, right? It is independent of the physical, dimensions of the material, right? Whereas if we were to apply the force on the y-axis, the crystal, we call it the crystals, we say that the crystal exhibits transverse effect, which is very similar to the the longitudinal effect. The key difference is the charge developed is not only proportional to the force, but also it is proportional to the xy plane dimensions. So this, I would request you guys to think, why this happens, why in the longitudinal direction, when you apply the force, the charge is independent of the material dimensions, whereas in the transverse axis, the charge developed, there is a dependence not only on the force, but also on the dimensions of the crystal in the xy plane. Right? Please think about it. But this is how we define our axis, and these are the properties, right? So the key takeaway is how we define the z-axis, the x-axis, and the y-axis, and how the piezoelectric behavior is different, or how it shows up as a longitudinal effect versus transverse effect, right? So again, going back to the axis definition, and we're going to deal with this more and more because all the subsequent maths that we will be doing will be based on the axis definition. So what we are doing is our x-axis, we will name that as axis 1, or y-axis as axis 2, and the z-axis as axis 3, right? And on top of it, because we are dealing with mechanical forces, and forces, as we know, can be like, the normal compressive or the tensile force, or it can be shear force. So the angular forces are shown as the fourth, fifth, and sixth axis likewise. So this is straightforward, right? So you can see along the x-axis, if you were to look at the x-axis in this direction, this axis is defined in anti-clockwise manner, right? And so is the fourth, fifth, and the sixth axis, right? Now, as we have been saying in very simple terms, right, that the charge that is developed is proportional to the force, right? In very simple terms, that's what we said in the previous slide. That if we are looking at the longitudinal effect, the charge developed is proportional only to the force applied on the electrodes. I mean, on the piezoelectric material. The charge that you see on the electrodes is proportional only to the force and nothing else, right? Now, if we were to divide this equation on both sides with the area A of the material on which we are applying the force, right? So then we can write the same equation as P is equal to D times sigma. And sigma is, we know, right? It's the stress, right? Sigma is force per unit area. And D is nothing but the piezoelectric coefficient. So we introduce the coefficient here by the name piezoelectric coefficient, and so D is one very important coefficient which we are going to talk about more and more. So nothing like kind of too big right away, right? It's still pretty simple. The charge, and P, by the way, we call P as polarization, which is nothing but the charge density. So the charge per unit area, Q, the charge per unit area that is developed is proportional to the force per unit area, right? And that is a very simple equation. We write it in the form P is equal to D times sigma. Now, key thing to note is the P is a vector, right? We can P is polarization, and polarization means there is a direction we are talking of, right? And similarly, when we talk of the stress that we are applying, when we talk of force is also a vector, and area is also actually a vector, right? So, for example, if we have a plate in this direction, so let's say this is a two-dimensional surface we have on this, right? So the vector of the area vector is normal to the surface, which in this case is the x direction, right? So the area is also a vector. So if we write this in a little bit more general form, where Pi, which is the polarization developed on the ith axis, and when we are talking of electric field, right, there are only or polarization, there are only three possible axes that are possible, right? I mean, on axis 1, 2, and 3, right? We cannot have, unlike the mechanical forces where we talk of 6 axes, because we have the compressive or the tensile stress, or we have the shear stress, right? Which we mean by the axis, the electrical field. there are only three directions, right? So the general form, we can write the general form of the polarization vector as pi, the summation of di times sigma k, right? And k, as we know, we have defined the 6 different axes. Sigma, we are talking of mechanical quantity here. So we have 6 axes to talk about. And we have a coefficient dik. Now, so if we were to write in a matrix form, and so what we actually, I mean, in this simple equation, what we are trying to show is the polarization in the ith direction. So it can be in the first axis or the second axis or the third axis is proportional to the stress on these 6 different axes, and the proportionality constants are given by these dij kind of coefficients, wherein we define dij as the polarization coefficient in the ith direction. So the first guy, I, is nothing, it denotes the electrical, it denotes the electrical direction, right? And J denotes the mechanical force that we are applying. Right? So polarization coefficient in the ith direction due to the mechanical force on the J axis, right? So in a general form, piezoelectric characteristic can be defined simplistically, and this is just, like I said, I think this is still pretty straightforward. Nothing, we are going to get into much more complex stuff, but to start with, this kind of sets the basic mathematical relationship to show how mechanical force results in an electrical quantity. So this equation, can somebody tell me, does it show the direct effect or the inverse effect of the piezoelectric material? When we are writing the equation in this form, are we talking of the direct effect or the inverse effect? Anyone? Is this a direct effect or an indirect effect, or rather the inverse effect of piezoelectric behavior? You can take a shot at it. I mean, there's nothing wrong. So maybe Ayush, why don't you take a shot at it? Ayush, are you there? If you want to take a shot at it. Nobody's answering.
Hello, sir.
Yeah, hi.
Sir, I have a network issue.
Okay. So we can say whether by this equation we are talking of the direct effect or the inverse effect. Okay, maybe someone else. There's nothing, I mean, nothing to get scared, right, on this. Anyone can answer. So maybe, let's see, Vishesh, you want to take a shot?
Sir, actually, your voice is cracking for me.
Sir, can you repeat the question?
Yeah, so the question is, this equation that you have written here, are we, so as I mentioned, right, so even if you look at the historical context, right, we said, what I said was, Madame Curie, the French physicist, right, they discovered the effect in 1880, and the existence of the reverse or the inverse was predicted by this gentleman Lippmann in 1881. And in that context, we talked about what is the direct effect and the reverse effect, right? So the direct effect is, which is obvious, right? I mean, if you think someone is discovering such a phenomena, what he or she would have done. Um, um, by the way, these were also two brothers, I believe. These were also two brothers. I'm sorry.
Hello, sir.
Probably. Yeah, hello, can you hear me?
Sir, your voice is not clear.
Oh, really? Yeah. Is it the case with everyone? Like my voice is not clear to everyone, or I'm sitting in a proper institute lab.
Sir, it's not clear for me either.
Oh. Okay, so let me. So what shall I do? Shall I leave and join the call, or? Okay. Let me leave and join the call once again.
Now it's clear, but like in
Clear?
between it is.
Yes, sir.
Okay.
Now it's clear.
Okay. So the point is this. So when common sense, right? Normal common sense, right? When this physicist invented or rather discovered this phenomena, what do you think they would be doing, right? They would be probably putting some pressure or force or whatever, and they would see that, oops, looks like we are seeing observing some charge, right? So that is what we call as the direct effect, right? And that is what, in normal common sense would tell, right? I mean, you are not going to take a piece of material and start applying voltages in all direction and try to see what is going on mechanically. Typically, that's not what you will do. Typically, what you will do is probably try to apply a force and see how the material properties change, right? So going with that logic, the question that I had is, if you look at this equation,
Mr. Sir, your voice is started cracking again.
let me see. One second. So is this better now?
Yes, sir.
Is this better? Okay. She was using a headphone. Okay. So this equation that we have written here, right? So this equation describes the direct effect or the inverse effect. A very simple question, right? And you should be able to tell the answer just by looking at how we have written the equation.
Direct effect.
Now is the question clear? Yes, Shakshi. Now is the question clear?
Yes, I think it represents the direct effect.
Right. And why is it direct, Shakshi? Would you give your reasoning for that?
Yes, because what polarization we are getting in the direction of the pressure applied, and the piezoelectric constant is a scalar, so the direction will be the same.
Yeah, so yeah, you're right, but let me probably mention this a little bit more mathematically. So if you look at this equation, right? So we have written this equation as y equal to fx, right? Function of x, right? And x we call as the independent variable, right? And y is the dependent variable, right? So if we look at the right-hand side of our equation, which is our independent variable, we are talking of a stress here, right? Sigma, which is a mechanical quantity. So we are applying the mechanical quantity or the independent variable coming on the right-hand side, and as a result of that, we are getting electrical phenomena by the name of like we are calling it polarization, electrical polarization, and that is the dependent variable, right? And that is dependent on force, right, or stress. So effectively, this equation is talking about the direct effect, right? So as we will see, once we start writing, going into the characteristics more and more, right, these equations will probably become a little bit more involved, and we'll see how the equations are written in different forms. So this is just a kind of a brief overview of what we are going to kind of discuss in the next few classes in great detail. So, so this is the transducer arrangement. If you see, we have a silicon or a quartz wafer, silicon dioxide wafer, and we have a metallic electrode, right? And why do we need the electrode in the first place? Any idea why we need the electrode in the first place? By the way, I would like you to see that I have been consistent with the axis definition. So the x-axis is the way we have defined in the previous slides, and the z-axis is the optical axis. So the x-axis is nothing but the electrical axis, right? We talked about it. And the x-axis is the mechanical axis, and the z-axis is the optical axis, right? So what you can see here, that in this arrangement, we have taken a quartz wafer with metallic electrodes being placed on the face, on both sides of the x-axis, meaning, or rather, the electrodes have a vector on the x-axis, right? And we have an amplifier and driver. We'll look into the details of how the amplifier should look like, and we'll go into that later. And as we discussed earlier, if we apply a force on, so this Qx, yeah. Qx equal to d11 fx, right? So so this we talked about longitudinal effect and the transverse effect, right? So this, when we are talking of this axis, I mean Qx is the axis, I mean the charge that is developed on the plates on the x-axis, right? And fx is also the force applied on the x-axis. So we are talking of which effect, the longitudinal effect or the transverse effect? Anyone?
Longitudinal.
Yes, we are talking of the longitudinal effect, right? Very straightforward, because the charge also we are observing, or the electric field associated with the charge that is developed, is also in the same direction, same axis, x-axis. For example, let's say we have a positive charge developed on this plate and a negative charge developed on this plate, right? So the electric field will be from which direction? The electric field will be from where to where? To be from here to here, right? Positive to negative, right? So it is in the same axis as the force that we are applying, right? So we are talking of longitudinal effect. So if we were to, and by the way, so coming back to the question, why do we need electrodes? Any idea why do we need electrodes? Metallic electrodes. So what kind of a material is quartz, do you guys think? Does it have high mobility? Is it a good conductor of electricity? What sort of, any idea on what sort of material is quartz?
Poor conductor of electricity.
Coming in, please.
Poor conductor.
Right. So basically, the reason why we need an electrode is we need to have a mechanism wherein we are actually connecting. So when we have these charges developed on both the sides, right? Essentially, we are going to analyze, or we are going to study how much charge has developed, right? So we will be connecting these electrodes with a like let's say wire, as I have shown, right? Now, because the quartz by itself is a poor conductor, we have a metallic kind of arrangement which allows, it kind of passes the information from all corners of the electrode to a single point. We can, the piece of metal allows a good piece of conductivity on the plate, so as when we are quantifying the charge that has accumulated on the material, we can study the, we can quantify the full charge, right? And we have passed this to an amplifier, and we'll talk about in more detail what sort of an amplifier it will be. And the amplifier will give a voltage, right? So essentially we will have the voltage as a function of the force. So this is actually a cool thing, right? We have been able to translate, or we have been able to move from the mechanical domain to the electrical domain, right? And the reason why this is cool is, see, our world that we live in, right? Those are all like, things like, it's a mechanical world, right? I mean, whatever signals, whatever things we do, right, are in the mechanical domain, right? But whenever we are analyzing, or when we are studying, or when we tend to go into the electrical domain, right? So that's why this kind of material becomes very interesting. It has generated an electrical information from a mechanical quantity, right? And this is one important reason why, over the last century or so, right, these material has got so many uses now. So anyway, going back to basic equations again. So because we have two plates associated with this piece, we also can associate a capacitance with this arrangement, right? We have, as you see here, we have the positive and the negative charges that has accumulated on the two sides of the material, right? And so that means we can also talk about a capacitance associated with it, right? And the capacitance is nothing but, we know, right, epsilon, which is the permittivity, and the area. Area is what? Area of the plates, which is nothing but the length, right? I have shown the length here, and the breadth B, right? And epsilon A by D. D is the distance. In this case, I have not used D because we are using D for something else. So we have used a parameter called T. T is the thickness of, or rather the distance between the two plates, right? So the capacitance associated with this arrangement is given by epsilon LB by T. Again, not a big deal, right? Very simple equation, right? You have done much more complex stuff when in class 11, 12, right? So, so what is the voltage that is developed? Let's say the amplifier doesn't have a gain. It's a unity gain amplifier, meaning whatever voltage appears at the input, it gives the same voltage at the output. Somebody can ask them, why do we use the amplifier in the first place? We'll see why we use the amplifier. But let's assume that the amplifier is a unity gain amplifier. Everybody understands, right, what we mean by unity gain, right? Unity means one, and gain means, so basically, if you have a voltage V in, so unity gain means V out will be equal to V in. So the gain is one, right? So the Vx is nothing but Qx by Cx, pretty simple, and which we can write as D11 sigma xx T by epsilon. So now, if we see here, we have, so Vx is nothing but, so the potential difference between these two plates, right, which is proportional to the electric field, right? Right? E is equal to V by what? The electric field is given by what? V by, or can somebody tell me the relationship between the electrical field and the potential?
V by D. V by T.
V by T, okay? So if we see here, so we do Vx by T is equal to, we introduce another term here, another coefficient called the G coefficient, and we'll see why we are bringing in more and more coefficients, because if you were to, as electronics engineers, when you are building systems, you will be buying material from different companies, right? And different companies, they use different parameters to quantify the performance parameters, right? So these coefficients like D or G, or you'll introduce few more. You will see these parameters are used to quantify the kind of product that you're going to buy from these companies, right? So we introduce another coefficient by the name of G. So the electrical field E is equal to G11 times X, right? And which means the relations, if someone says that, okay, this is the D11, we should be able to, and if you know the permittivity, we should be able to derive G11 from these, right? So not a big deal, but it's important to know how these coefficients are dealt with, or how or in which context the coefficients are referred. So G11 is equal to D11 by epsilon, and epsilon is nothing but epsilon 0. So this is the absolute permittivity and this is the relative permittivity, right? These are straightforward stuffs, right? Epsilon, the actual permittivity of the material is given by epsilon 0, epsilon r, right? So I think we'll probably take one more, we have a few more minutes left. Or maybe we stop here today. We'll stop here today and then we'll talk about perovskites in the next class, in tomorrow's class. Right, guys? And yeah, so thank you. So I will upload this video. And if you have any questions, you feel free to drop me an email, or we can, discuss tomorrow again in the next class. We'll start with perovskites tomorrow. Okay? Thank you.
Thank you, sir.